All right. 7 will be one of them. So we're on page 445, number 7. Okay, number 7 looks like this. Okay, it says 3 log base 2 of x minus 1 plus log base 2 of 4 equals 5. We'll take a look at that one, and then if you want to look and find another one, we'll do that one as well. So I think I helped somebody with one like this, or this one the other day, and what they did is they did this. They said, well, hey, this is addition, and logarithms allow us to change addition into multiplication, so they wrote this, log base 2 of 4x minus 4. They multiplied these together. Okay, is that okay? Okay, it's not okay, and here's why. See that 3 right there? It only applies to this logarithm right here. If we multiply these together and then still have the 3 out front, doesn't it make that 3 apply to the 4 also? Yeah. It does. Okay, so that's not the right way to do it. It's not a bad idea, but it's not the right way to do this problem. The first thing you want to do with this one is move this guy up here. So we're going to write this as log base 2 of x minus 1 cubed plus log base 2 of 4 equals 5. And then I'm going to continue writing it as one single logarithm. So I'm going to write this as log base 2 of 4 times x minus 1 quantity cubed equals 5. Now, if you take a look at here, at this point right here, you'll notice that the 3 only applies to the x plus 1. It doesn't apply to the 4 like it would have before if we did it in the wrong order. Okay? All right. Now, at this point, there are two things that you could do. You could simply, right now it's in logarithmic form, and if you can't figure it out, you write it in exponential form. Okay? Or we could undo the logarithm. How do we undo the logarithm? Yeah, raise each side so take each side and exponentiate with a base of 2, so like this. Okay? This function is exponential base 2. This function is log base 2. They undo each other. So I have 4 and then x minus 1 quantity cubed. And over on this side I have a 32. Right? And then I just keep solving this. So I'm going to divide both sides by 4. So even though this started out looking really, really awful, this is just an 8. And the cube root of 8 is 2. So we're taking the cube root of both sides. Again, keeping in mind that we're learning how to undo things, inverse operations. So this is going to be x minus 1, and this is going to be a 2. So we finish this off by adding 1. So I get x equals 3. Now, do we just blindly circle that answer, write it down in the answer space on the test, and say, hey, Mr. Lass, here's your answer? Nope. Okay. If an original equation has a logarithm, an even root, or a division in it where the variable's in the denominator, you want to check and make sure that it's okay that we actually plug this in. So if I take this 3 and put it right here, 3 minus 1 is 2. I'm taking the log base 2 of a positive number. That's going to be okay. It's going to work out just fine. Okay? So that is the answer. Okay? We don't have to cross it off and say that it's extraneous. Okay? Okay, we're correcting this on Monday. Okay, I'll do one more problem. Okay, 29. Okay, so let's take a look at number 29. Okay, 29 is on the next page, so we're on 446, and 29 says this. It's 5, and then it says 2 to the 3x equals 8. Okay, let's see. If this were 5, and then we had, say, the 4th root of 3x equals 8, what would you do first here? You divide both sides by 5, right? And then we'd have the 4th root of 3x. And how would we undo the 4th root? 4th power. 4th power. We'd raise both sides to the 4th. Okay, using those inverse operations. So the first thing I'm going to do on this one is I'm going to divide by 5. So this is going to be 2 to the 3x equals 8/5. Okay, now this is a function right here, just like that's a function. Okay, and we know how to undo roots. We raise things to power. So we undo the fourth root by raising it to the fourth power. If it were the seventh root, we'd raise it to the seventh power. What function is this? What is it? It's exponential base 2. How do you undo exponential base 2? Log base 2. So I'm going to take the log base 2 of this side, and I'm going to take the log base 2 of this side. Why is this algebraically a legal thing to do? Why is this okay? We're doing the same thing to both sides, okay? In your algebra class, teacher probably taught you that's the golden rule of algebra. Whatever you do to one side, you always do to the other side. So this function right here undoes that function right there. So over here, we get a 3x. Over on this side, we have log base 2 of 8/5. Now, to finish this off, to get x completely by itself, what do? Divide by 3. So we divide by 3, cancel these off. So I get x equals, now this is a bit of a mess. You can leave it like that if you want. I mean, technically this is just a number divided by 3, so there's no problem with that. If you wanted to maybe make it look a little bit nicer, it would be 1/3 of log base 2 of 8/5. Okay, that might be a little bit better. Okay, but either one's okay. Could you do this? Would that be okay? Yeah, that would. Could you change them to LNs? Sure, you could change them to LNs. Yeah. Now say that again. 2 to the 8/5. No, well that's not what this means. Okay, this isn't. This right here isn't a. It's a base of a logarithm, not a base of an exponential. Okay, so this isn't an exponent. It's the number we're taking the log of. Okay, everybody good there? Okay, watch. This is perfectly fine, but remember I said, I mean, if you're going to plug things into your calculator or get a decimal approximation at some point, you might as well use logarithms that are on your calculator. So at this point, what if I took the ln of both sides? Doesn't that still have the property where I can move this out front? So this would be 3x ln 2 equals the ln of 8/5. This is just a number. I can type that into the calculator. How do I get the x by itself? Divide by, I don't want the 3 and I don't want the ln of 2. So those would cancel and I get x equals the ln of 8/5. And I get, well this is, let's move this up here. Couldn't I write this as the ln of 2 to the 3rd, which is 8? Would that be okay? And couldn't I write this as the ln of 8 minus the ln of 5 over the ln of 8? Wouldn't that be okay? That'd be fine, wouldn't it? Okay. Which one looks better? 1, 2, 3, or 4? It's really personal preference, okay? But if it were my preference, I'd say 1 probably looks the best. They're all very simple logarithms. ln of 8 minus the ln of 5. We put that in parentheses on the top. Divide by ln of 8. Okay, now can I cancel the ln of 8 with the ln of 8? No, because this one is a term. Okay? All right, keep that in mind. Yeah?
How did you get 2 ln of 8? Or 2 ln of 8s?
Oh, I used the quotient property. I changed division into subtraction.
Yeah, but where'd you get the one on top?
I moved this up here, so it was 2 cubed. I used the power property there. Okay? So that's the good and the bad thing about logarithms. There are lots of ways to write things, and there are lots of ways to write things. Okay? All right. Any questions? Okay. All right. Go ahead and put that away, please. You're going to need a calculator today, so you take that out. if you would figure out the first question there, that starter question, double check your answer with your neighbor again, grab your calculator, get that out because you're going to use it a lot today. And if you happen to not bring it today, make sure you bring it on Monday because we're going to use it again then. Probably first learned how to do these in maybe 6th or 7th grade. Shelby, what do I type in the calculator?
I put 5%
Okay, how did you type 5% into the calculator? Okay, so Shelby put 5 in the calculator and hit the percent button. Okay, which is totally fine if you have a calculator with a percent button. I don't, so help me out here. When you hit 5 and then hit the percent button, what did the calculator do to the 5? 0.05. Okay, so we move that 2 decimal places. Okay, so we move that to the left 2 places. 0.05 times 2756. Okay, the word of means multiply. So 5% of that. We naturally change this into a decimal. Okay, that's how the calculator is going to compute this, and we get 137.8. Everybody got that right? Okay, excellent. So we got 137.8. Okay? So what we're going to work on today is something called compound interest. Okay, now interest is just a fact of life. Okay, most of you are going to get a loan at some point, if nothing else, maybe on a car or on a house or something like that, and you're going to pay interest. Interest goes both ways. Okay, so let's talk about what interest is. Okay, interest is the amount of money paid for the privilege of borrowing money. Quite an entourage.
That's all for your haircut.
All right, there we go. Okay. Quite a crew. Go ahead and have a seat wherever you'd like. Okay, so interest is the amount of money paid for the privilege of borrowing money. Okay, now this goes both ways. It can be a good thing or it can be a bad thing. Okay, it's a good thing when you get paid the interest. So if you put money in the bank, a lot of you might have a savings account or maybe a checking account or something like that. If you put money in the bank or in the stock market or you put it in an investment of some sort, you get paid the interest. So if you have a grandma or grandpa who put $100 in an account or something like that, that's going to earn interest. You're going to be paid interest. Essentially, the bank is borrowing money from you. Okay? So that's good when that happens. It's bad when you have to pay the interest. Okay? And you'll pay the interest when you do a car loan, get a mortgage. What's a mortgage? Okay, it's a house loan, okay, fancy name for a house loan, or when you do a student loan or something like that, okay? Whenever you borrow money, you're going to pay somebody money for the privilege of borrowing that, okay? All right, so the simplest type of interest, not surprising, is called simple interest, okay? Nice, easy name. Okay, with simple interest, you're paid a set percentage for a set amount of time. And here's the key, you're only paid that interest at the end of that time. They only pay you interest once. So one time. Okay, now there's quite a bit of vocabulary that we need to go over in order to understand all of this stuff with compound interest. So let's talk about what the principle is. And I think I spelled principle wrong. I think it's L-E. Yeah. Okay? It's always nice to make a mistake in front of lots of people. Okay?
Jonathan, would you take a minute and
Sure.
just explain to them what technology you're using?
Sure. So this program is called PDF Annotator, and I can pull up a blank screen and just start writing on it. whatever you want, forgive my penmanship, okay? I can pull that up, and at the same time, this is being recorded. So everything that shows up on my screen gets recorded, and it'll be posted on a website. So these students can watch this lecture again and pause it, go back and watch it anytime they want. They've got access at any time they've got access to the internet. So how many of you have watched videos outside of class? Okay. So nearly everybody in the class will access these at some point. So I can just flip back and forth, and we're right back to the lecture.
How many of you find an advantage to being able to go back and rehear a lecture?
There we go.
In math.
Yeah. Okay. And the cool thing about this is you can just, I mean, this is just a stylus. You can just flip it over and it erases. And this is being recorded. Everything on the screen and then everything I say is recorded here. So kind of fun. Okay, so let's talk about what the principal is. The principal is the original amount that's borrowed or invested. So if I say principal, we're just talking about the amount that's put in the account. So if your grandparents put $100 in an account, we'd call that $100 the principal in the account. Okay, and then we use R for the interest rate. Okay, and that's again short for interest rate. And Shelby can help us out. This is always entered as a decimal. Okay, so we always enter the interest rate as a decimal. Okay, and if you've seen simple interest, which I'm sure you have before, does anybody remember the formula for this? You're going to recognize it when I write it up here. It's I equals P RT. Okay, I equals P RT. So we're going to do an example here. We're going to put $1,000 in an account bearing simple interest. Okay, 8% per annum. What does per annum mean? Per year, annual interest for 50 years. Now, that's a long time. It's quite a bit of money at this point in your life. Okay, we're going to put it in there for 50 years. So you can't get this money out until you're 67-ish, right? Okay, so that's going to be a long time. Let's see how much interest is due at the end of that time. So the formula is really, really easy. The interest is going to be the principal. P stands for principal. What's the principal in this case? 1,000. Okay, so we put in $1,000. Okay, so 1,000. Okay, the interest rate. Shelby, what are we going to put in as the interest rate? 0.08, right? 0.08. And then T stands for time, just like any other equation that we've got or formula. We're going to put that in for 50 years. So grab the calculator. So we're going to put $1,000 in at 8% for 50 years. $4,000. Okay? So we end up with $4,000. Okay, now, listen very carefully, because this formula is different than all the other formulas that we're going to use today. In fact, we're going to adjust this in just a minute. Okay, how much is in the account after 50 years? It's $5,000, isn't it? Because they put $1,000 in there to begin with. This formula only computes the amount of interest that the bank's going to pay us. Now, again, for the first year and the second year and the 10th year and the 49th year, there was $1,000 sitting in that account. When did we get that extra $4,000? At the very end of those 50 years. So $1,000 sat in there for 50 years, and at the very end we said, hey, we'd like our money and our interest. So we go in there, they compute the interest, they do this calculation right here. They say, hey, we owe these people $4,000 for the privilege of borrowing their money for 50 years. So they're going to give you the original $1,000 back plus the $4,000. So altogether, we get $5,000 bucks. $4,000 in interest, $1,000 was the original principal. Okay? So what is the amount of money in the account after the interest is paid? That's $5,000. Okay? Now, what would be really nice is if we just had a formula that said, look, tell me how much is in the account, because that's really what we're after, right? We don't want to know just the interest, we want to know how much is in the account. So let's start with this formula right here. Okay, the amount in the account would be the original principal plus the interest. Well, let's take this formula for interest and let's put it right here. So this is going to be P plus, what's the interest? PRT. So we could write this A equals P plus PRT. But it probably would be a lot better. Rather than putting P in both of those places, let's do this. Let's factor it out. So this is going to be P, and then what's left when we take a P out of this? A 1 plus RT. Okay, and that formula would give us the answer just from the get-go. So let's do this. In our example right here, what was the principal? 1,000. Okay, and then let's do 1 plus, what was the interest rate? 0.08. And then we're going to multiply that by the time of 50. So let's type that in the calculator. So we're going to do 1,000. And then parentheses, 1 plus 0.08 times 50. Now, if we did this correct, this should tell us the amount in the account after 50 years. We already know the answer. What should the answer be? Should be 5,000. Let's hit enter, and it tells us it's 5,000. Okay, are there any questions there? Yeah.
When you simplified A equals P plus I, where did you get the 1?
This one right here?
Yeah.
We factored a P out of both of those, so when you divide by P, you're left with a 1. Okay, anything else?
Just a
Sure.
quick thing on the calculator part of the technology.
Okay, so this is a TI-83 calculator. It's what's called a calculator emulator. So it looks just like, so somebody hold up your calculator. So it looks almost identical to their calculator. So they can see what buttons I'm pushing. And this little program right here that follows my cursor is called, I think it's called Pen Attention or Cursor Attention. It's just a free download. You can download these free on the internet. And it just makes it easy for showing students, you know, what buttons I'm clicking. There's also a program that you can get that has an additional screen off to the side here that keeps track of what buttons I've pushed, and it keeps a key strike history, so they can see when I hit equal, what buttons I pushed, and all that sort of stuff. And that can be helpful sometimes. But we're doing pretty easy calculations, so it's pretty easy to follow. Good? Thank you very much. Hope you enjoyed that. Okay, I want to point out one quick thing. Why is that 1 there? What does that represent in this problem? Okay, that represents the original amount of money. Okay, what is 1 as a decimal? 1.00, right? What's 1 as a percent? Yeah. What is it? Somebody said it back here. 100%. It's 100%. Okay, this 1 right here, and this is going to be really important for the stuff we're going to do down the road. This 1 right here represents 100% of the money that you put in there to begin with. So you get 100% of the money you put in to begin with, plus this piece right here, that's the interest that you get. Okay? So whenever you see 1 in an interest formula, just realize that represents 100%. You're going to get all of the money you put in plus some interest. Okay? So when you see that 1, 100% of what you put in plus the interest right here. Any questions there? Okay. All right. Let's take a look at this then. Yeah.
So does that relate to like what you would do with like a CD?
Exactly. Mm-hmm. Yep. Yeah, we're gonna do problems just like that. Okay.
And
CD,
is that
certificate
a
of deposit.
reasonable interest rate like now? Like,
No, not now. No. The bummer is, so 10 years ago that was a decent interest rate. Now, does anybody have a savings account? Okay. Do you know what your interest rate is?
like 0.0006.
If you have a savings account, your interest rate is probably about 0.25%, 0.25%. So if you wrote that as a decimal, 0.0025.
What?
Okay, it's tiny.
Sounds like
Okay.
a
Three seconds.
Yeah, and some of them are even less than that. They're like 1/10%. Okay,
Is that the same for CDs though?
CDs are a little bit better. Okay, they might be in the 2 or 3% range. Okay, yeah, there you go.
Horrible.
Does everybody know what a CD is?
Again,
Certificate of deposit. That means you're going to put your money in an account and they're going to pay you interest. It's going to be compounded, which is what we're going to talk about next. Okay, so we'll get to that. There is a difference. Okay, a savings account, you can go in and get your money anytime. A certificate of deposit means you put the money in, you can't get it back without a penalty. Okay, until the end of that time. That's why they're willing to give you a higher interest rate. Okay, so let's talk about compound interest. Now, this is fundamentally different. Okay, and this is how most interest works. Simple interest like that, very, very simple. Okay. But you will not be able to find a simple interest account, okay? And you wouldn't want a simple interest savings account because they only pay you money at the very end for those 50 years that just sat there at $1,000 and they didn't pay you the money till the end, okay? So compound interest is different than simple interest, okay? Compounding is a fancy word that interest is paid and it's added to the account at set intervals of time, okay? And the key here is what makes a huge difference, and it is a gigantic difference, is interest is paid and it's added to the account while it's still earning interest. So if we take the example that we were looking at earlier, if we put $1,000 in there, rather than it just sitting there for 50 years and having no interest added to it, they're going to pay us and add interest to the account every couple of months, every year, or whatever it happens to be, okay? Now we're going to start off with a very easy example. We're just going to say it's compounded yearly or compounded annually, okay? So here's the example. $1,000 put in an account bearing 8% interest, compounded annually for 50 years. And it says compute the amount at this time. So we're going to use this formula right here, okay? So we're going to let 1 year go by. So in the beginning, we just have $1,000. Okay, now we're letting 1 year go by. Okay, every time we do this, we're just letting 1 year go by. So we're going to recompute here. So what was the amount sitting in the account for that first year? It was $1,000. Okay, and then we have 1 plus the interest rate of 0.08. And we let 1 year go by, so I'm not even going to write that. I'm just going to write this. That's how much would be in there. Okay? So we could grab our calculator and we could compute that. So this is going to be 1,000, 1 plus 0.08, $1,080. So at the end of the first year, rather than just saying, hey, thanks for leaving your money with us, they pay us how much in interest? $80, and they put it in our account. Okay? That is better. So for the second year, we're going to take this stuff right there. That's how much is sitting in the account for the second year. So that's the new principal. So here's the principal, 1,000, 1 plus 0.08. Okay, now that's just the principal, and then they're going to pay us interest. So this is how much was sitting in there. They're going to give us 100% of that plus 8%. Okay, I'm going to change colors here. This is how much is sitting in there for the third year. So that's the principal that's sitting in there for the third year. So this is going to be 1,000, 1 plus 0.08, 1 plus 0.08. That's how much is sitting in there for the third year, and then they're going to give us 100% of that plus 8%. Yeah.
Just take what the amount after first one was compounded.
Sure, yeah, you could put $1,008 or $80 and then times it by 1.08 and then 1.08 again and again and again. Okay, and that's really what we want to get at. is notice how many 1 plus 0.08s there are. For 2 years, there are 2. For 3 years, there are 3. What about 4 years? There'd be 4 of them, okay? So this would be 1,000 plus 1.08 raised to the t after t years. So for our problem, this is going to be 1,001 plus 0.08 raised to the 50th. Okay, now, don't type this into your calculator for just yet. Okay, I want you to think about this. Here's the only difference between this problem and the one we just did. Before, the $1,000 sat in there for the 50 years and they paid us interest only once, at the very end. With compounding interest, they're going to pay us interest every single year. So they add $80 the first year, probably a little more than 80 the second year, and a little more than 80 the third year, and so forth. So they're paying us interest every year on a little bit more money. Now, does that seem like it would make a big difference? Well, let's see. Yeah, you know what's coming, right? You're really,
It's going to be like
you got this all figured out.
$6,000.
Okay, so 1 plus 0.08, and we're, whoops. And we're going to raise that to the 50th, right?
6,000, 7,000.
$46,901. So how much did we have before?
1,000.
Okay, total was $5,000. At the end of 50 years, if they just pay us 8% interest every year and put it in the account, we get almost $47,000. Okay? $42,000 more than we would have if they just did simple interest. So does compounding make a difference? Okay, a gigantic difference, a huge difference. Okay? Now, this is just a very simple example. Very seldom will you find an account that pays interest annually. Okay, and that makes the numbers really easy to figure out. So the actual compound interest formula looks like this. Okay, so I want you to fill in these blanks. Okay, this is still P, and this is still 1 plus, well, what does the 1 stand for again?
100%.
You get 100% of what you put in there originally, and then we're going to do R over N raised to the N times T. Okay, now, P stands for principal, R is the interest rate, T is time. What is N? Okay, it is the number of times interest is paid per year. So if it's compounded quarterly, N represents the number of times it's paid per year. So quarterly, how many times per year? 4. N would be 4. If it's monthly, what would N be? 12. If it's daily, 365. And if it's hourly, well, gosh, we could figure that out. It would be 365 times 24, okay, whatever that happens to be. Okay. Now, I want to talk about what happens here. Okay, everybody watch, please. Okay, if we just took that original problem and said, all right, this is going to be 1,000 and then 1 plus 0.08, and we raise that to 4 times 50, they're going to pay us interest 200 times, right? But are they going to pay us the full 8% every time they pay us interest? No, that wouldn't be fair. It's 8% per year. If they're going to pay us 4 times per year, they're going to take that 8% and they're going to divide it by 4. So they're actually going to pay us, what's 8% divided by 4? They're going to pay us 0.02, or they're going to pay us 2%. Doesn't that seem fair? If they're going to pay us more times per year, they're going to break that up and say, okay, 8% per year will pay you 2% for the first quarter, 2% for the second quarter, 2% for the third, and 2% for the fourth. So by the end of the year, you're paid 8%. Now we're going to find that if they compound, it actually works out to be more than 8%, but we'll talk about that in just a minute. Okay, are there any questions there? Okay, does everybody understand how the formula works? Why this is fair? 50 years, 4 times 50, they're going to pay us interest 200 times, but they're not going to pay us 8% every time because they're going to pay us a fourth of that, 2% every quarter. Okay, so let's grab the calculator and see what difference that makes. So we're going to have 1,000, and then we're going to do 1 plus 0.08 divided by 4, and then we're going to raise that to the, and you have to have this in parentheses, 4 times 50. Okay, now, if they paid us 8% and put it in at the end of every single year, it made a gigantic difference. It got us from $5,000 up to $47,000. Okay, so now let's have them pay us interest more often. Let's do it every quarter. $47,000 to over $52,000, another $5,000 in interest. Now notice in every case, it's still $1,000 that we put in there, and it's still 8%. The only difference is how they pay interest. Okay? Makes a gigantic difference. Any questions at this point? Yeah?
Which is more common, them to do it quarterly or annually?
Quarterly.
Really?
Yes. Quarterly.
So even though it's only 2%, it's still better than annual.
Okay, 2% per quarter is better than 8% annually. Because they're going to pay you the interest. They're going to put it in there. Think of it this way. At the end of, so January, February, March. At the end of March, they're going to figure out what they owe you, and they're going to put that in the account. And even that little bit of money that they put in there is going to earn more interest the second quarter, and the third quarter, and the fourth quarter. So effectively, it's like they're giving you a higher interest rate. Okay? Does that make sense? Okay, occasionally you'll find a bank that will do monthly. So let's compute what it would be monthly. What's the only thing I have to do to the formula? Yeah, just put this as a 12. Change the 4 to a 12. So this is going to be 1,000. So what was this? This was 52,000 what? 52,484. Talking lots of money now. So 1,000 and then 1 plus 0.08 divided by 12 raised to the 12 times 50. Now think of it this way. 12 times 50. They're paying us interest 600 times. They're going to add a little bit of money to our account. It's less every time they add it. Okay, now notice you can just recall that last command. I'm going to type in a 12. I'm going to insert that 2. Now, it made a difference, but not quite what you'd expect. I mean, gosh, if we went from quarterly to monthly, I mean, they paid us interest 200 times before, and now they're paying us interest 600 times and adding it to our account. Okay, it seems like it ought to make a bigger difference, but remember, they're paying us a tiny amount of interest every month. Okay, so this is 53,878. Okay, do you think daily is going to make a huge difference? Okay, so I'm going to grab this, and all we're going to do is just edit this. Daily would be 365 times, so I've got to insert a 5 on both of these. Well, it's nothing to sneeze at. It's another $800 or so. Okay, so this one is 54,000. Thank you very much. 574. Okay? Now, if we did it every single hour, notice that the difference comes by just compounding. Huge difference by just compounding. If we compound more often, yes, it makes a difference, but not as big as a difference, not as dramatic a difference as if we just go from simple interest to compound interest, period. Even annually makes a gigantic difference. Okay? Quarterly, big difference. Okay, but not as big. Yes.
Where did the banks get the money to pay you this money? Put your money in.
So you put your money in, and they're going to pay you. So like right now, you're putting money in a savings account or in a CD, and you're earning maybe at the most 2 or 3% interest. They turn around that and they lend that people to buy a car or a house or something like that, and they're going to get 6% interest. So they make money on your money, and they give you a portion
They
of that.
loan out your money.
They loan out your
They
money.
charge people interest on it.
In essence, that's
So
what
they're
happens.
making money from your money.
Yes, that's right.
But you see, this is a business and a
Okay.
service, and you should know this before you give them your money. So that way you're willing to give them your money. You need to be
Touching me
informed.
is proving your point.
Yeah, be careful there. Okay, any questions?
Shaking.
Okay. Well, so this begs the question, what if we could pay interest not every hour, not every second, but all the time, like continuously? Just add tiny, tiny amounts of interest. Okay? There we get to something called a continuous compound interest formula, and it looks like this. And a number crops up that we've seen before. It's the number E. So this is why this is in the chapter where we study exponentials. Because if you do continuous compound interest, here we've got a base. This is an exponential. It's 1 plus some tiny little decimal number. Okay? That is an exponential. If you pay interest on a continuous basis, we get this continuous compound interest formula that looks like this. There are lots of things that change continuously. Take, for example, in a normal situation, home prices or stock prices. They generally can change on a continuous basis. Okay? It's not like at the end of 4 months, your home price goes up this set amount. Okay? They change on a continual basis. Okay? So that's a decent example. We're going to do some examples in 6.7 where things actually change on a continual basis, and we'll use a formula that's very similar to this. Okay? So let's put $1,000 in an account for 50 years at 8% compounded continuously. And again, the word here that's very key is continuously. If they say continuous, then you use this formula. If they just say compound, then you use this formula. Okay? Again, those are the key words. Compound, use this formula. If they say continuously compound, then you use that formula right there. So we're going to put into our calculator this formula. It's going to be $1,000, and then it's going to be, E raised to the 0.08 times 50. So we'll throw that in the calculator and see what we end up with. So we're 1,000. You can either use E, that's by the divide key, or the second function on the ln key, 0.08 times 50. This was daily interest, and this is continuous interest. It only makes a difference of about, what's that, $24? Yeah.
It only makes $1.
What? Oh, okay. So Josh went through and he computed what it did for an hour, and it only makes $1 difference. Okay? So if you paid interest every hour versus paying interest every millisecond, it only makes $1 difference in the end. Okay? So again, the powerful thing is compounding over simple interest. Okay, any questions there? So 54, 598, is that what it was? 598. Okay? Either way, we'd like to have that money, wouldn't we? Okay. All right. So let's talk about why it works this way, okay, and what effect this has. Okay? Compounding is a lot better than simple interest because it has the effect of making the interest rate appear higher than it actually is. There was nothing wrong with the simple interest that we did before. Okay? When we ended up with $5,000 at the end of 50 years, I mean, that's not a kick in the pants. I mean, it's better than just the $1,000 that was sitting there to begin with. Okay? But it was much better if we compounded. It has the effect of making it a higher interest rate. Okay? So you may occasionally hear the words effective rate. Okay? Or it's sometimes also called the yield. If you go into a bank and look at the fine print, a lot of times in the banks or credit unions, they've got posters saying, hey, put your money in a CD or put it in our savings account. It'll say APY, annual percentage yield. Okay? They're going to want to tell you what the effective rate is. By law, they have to advertise the actual rate, and then they can tell you what the effective rate is or what the yield is. Okay? Now they're going to want to tell you one over the other. They're going to want to make a big deal of one as opposed to the other, and we can figure out what that is. Okay? So the easiest way to figure out what the effective rate is to use $100, because that's a nice easy number. It's also like a percent. Okay? And 1 year as the time, and then compare what you end up with to the nominal rate or the original rate. Yeah.
What if I don't have $100?
Let's just say you do. Okay? Because you're also not going to find somebody that pays you 8% interest right now either. Okay? All right. So it says, what is the effective rate of 8% compounded quarterly? So again, the formula we're going to do is, it says compounded. Does it say continuous? Okay, not on this one. It says compounded quarterly. So we're going to use A equals P, 1 plus R over N raised to the NT. Now, how much did I say we were going to put in there? $100. Okay? The interest rate is 0.08. What did I say to use for time? 1 year. And because it's quarterly, what is N? N's 4. So we've got this entire problem set up. So this is going to be 100, 1 plus 0.08 divided by 4 raised to the 4 times 1. Or just raised to the 4th. So let's type that in the calculator. So I'm going to clear this off so this looks good. 100, 1 plus 0.08 divided by 4, close the parens, and then the exponent is going to be, now I'm going to put this to the 4 times 1 just to drive home the point. N is 4 in both cases, and we're doing this for 1 year. Okay. 108.24. Now, if they had just paid us 8% for 1 year and we put $100 in there, how much interest would they have given us?
It's $8.
They would have just given us $8. What's 8% of 100? 8, right? See why 100 is easy to use? Okay. It would normally be $8. Okay, but we got $108.24, right? Do I need to round up? No. Okay. So the interest they gave us was 8.24. Now make a comparison. This is 8%. Effectively, what would the interest rate have been? 8.24. Okay? All you have to do is shave off that 100 part. Just take the 8.24. That is the effective interest rate. So the effective interest rate is 8.24%. So compounding quarterly has the effect of actually paying 8.24% per year. That would be the effective rate or the yield. Okay, now if you go into a bank or a credit union, which one are they going to make a big deal? Are they going to say, hey, we'll pay you 8%, or are they going to say, hey, your yield is actually 8.24%? They're going to emphasize the yield because effectively that's what they're giving you. Okay? If they just gave that to you at the end of the year, that's what it would be. Okay? Now, what's the key word on this problem right here?
Continuous.
Continuous. So what formula are we going to use? Whoops. A equals P e to the RT. So this is going to be $100 e to the 0.08. What's the year? What's the time? 1. So we're going to type that in the calculator. So we're going to do 100 e to the 0.08. Okay, whoops. What's the effective rate? 8.32%. Okay? That would be the effective yield, and that's why. Okay? When you compound, it has the effect of making the interest rate seem higher. Any questions? Yeah?
Is that something you get excited about, that the continuous rate is that much?
No, because you won't find anybody that pays continuous compound interest. Okay? You'll find it monthly and quarterly, nothing else. You can get started on the assignment. Please do. That's enough to do probably half the problems. We're correcting 6.5 on Monday, so please make sure you're ready to go there.
Why does it seem like you're making a big stink of that?
It's nice to see